So I'm going to talk about the failure of Python object serialization. I'm Mike McKerns, and I actually, oh, thank you. Now I get to, is this good? Is it on? Okay, so I get to work a lot with some project basically that's been funded over the course of 10, 15 years with the NNSA, Air Force Office of Research, Department of Energy, NSF, and several partners. So it's I do risk and high performance computing, and I wanted to start with a little bit of magic before we get into slides, right? I'm probably most known now for the dill serialization package, which can serialize pretty much the entire Python language and most of the most common constructs, programming constructs that people use. So if you can look, I prepared this in the interpreter ahead of time so I didn't have to type it all out, but there's a double lambda which I use inside of a kind of a nested function. There's testmes inside of which is from the double lambda. I can do anything pretty much as complicated as you like. Then I build the object blah off of complicated, so that's actually the nested function on the inside. I build a class, change the class definition, so I build a class foo which has bar and y. I build an instance of it. I serialize an instance of both the foo object and the foo class itself. Just because I could, change the class definition, make another instance, and then do a dump session. So a dump session will save everything that I have in the interpreter session to a file. I didn't need to, but I just wanted to be able to start from here, and then I'm going to have to put this down. And then basically import dill and load the session, and then I should have g.z because that's the new definition. I should also have f, which is from the old instance, and I have f.y. And I can, since I had a serialized instance like that, f, I can even do dill.loads of f, and I'll call it something like f underscore, and I'd have that dot y. So I can do fairly complicated stuff. I think I had blah, I called it, blah, something like 12, which should, yeah. So the goal was to be able to serialize the entire, everything in the language in an easy way. So dill's able to be used by, so Python has use dill. There's a bunch of other things like MPI for Py has, they don't depend on it, but what they do is they allow people to override the serializer for dill in particular to augment high-performance computing. So it's been a package that's been around for a while. But I want to talk about why Python has high-performance computing problems and how to fix it. And so my first real venture into Python was high-performance computing. It was 2003. I was actually trying to use Python to prove that we could build the teragrid, which old folks like me will remember, and everyone else won't because I helped kill it. The idea is we didn't need new technology. We could do, like PyGlobus now is actually something that does current uses current SSH technology as opposed to inventing something new. And so the idea was to use Python and SSH technology to be able to put together a distributed grid of machines. And say, so I had some large projects, 15 million and 12 million for parallel computing frameworks. And what I built was pyina, which is a parallel map framework, parallel execution framework for MPI, cluster schedulers, pathos, which did the SSH tunneling, copying, execution, so you could do distributed computing. And the lab was, the idea was to be able to work between supercomputer centers and have a large-scale distributed parallel framework. The target being predictive science analytics, where I built a package called Mystic, which allows optimization at the large scale for predictive science, basically trying to predict things like structure property relationships, or whether some material, some bomb, something was going to hit some target, kind of things like that. The problem is when we put these high, the optimizers that were designed for parallel computing together with the parallel computing framework, it didn't work after we were done. It didn't work primarily because Python sucks at HPC. The reason was serialization. Because I built the thing to work in principle, but Python actually, the reason Python was chosen because it has a lot of the right properties. It does a lot of things right: dynamic lazy evaluation, mix of functional and object-oriented programming, weakly typed, many other good reasons. But the problem, as a lot of people will say, is it's got a global interpreter lock, right? The GIL. I mean, the GIL is just a the GIL, if you actually find out what it is, it's a read-only integer that when you start up the _main instance, it's built in C, and you can't change it, but it's referred to, and the stack, anything that's a stack object, execution stack object, a frame object, basically refers to that number, and you can't change it from Python. You can only change it from C. Anything that refers to the GIL, you can't pass to another thread, or else it fails. So there's parts of the language that can't be serialized, anything that has a yield, et cetera, et cetera. They have a very difficult time of being serialized because they refer to this one integer that's read-only, which is a pain in the ass. People know that, So you have good things from the GIL, like lazy function evaluations, lazy compilation, but then you have problems in that things like yield, iterators, generators, etc., parts of the language are not serializable. And therefore, since parts of the language were not serializable, I think it was very, Guido and others were very lazy in making sure the rest of the language was serializable. So in essence, actually, you can't serialize most of the Python language or most of the constructs. So any of us who've done any distributed or parallel computing, you find out, I'm building this cool thing, and all of a sudden it doesn't work because you can't ship an object. You can't pickle an object from one place to the other. So common workarounds are to use multiprocessing, but it still can't serialize a bunch of stuff. If you use C, basically through C types or Python, you can go to the C layer through PyC layer in the shared memory, or use no GIL. But like I said, most objects are not serializable. Most language constructs are not serializable, and that's really stunted the growth of Python on high-performance computing. But there are ways around it. Basically, there's, like I mentioned, use C types, and there's also source extraction. So if you can extract the source code of the object, dill, one of the things dill does is take any even dynamically created source code, dynamically created objects, and be able to pull the source code out of it, and therefore you can package it into another object that aids in serialization as well. There used to be just copy reg, and now there's reduce and get state, so those things help. You hear a lot of people say, well, don't pickle your stuff, it's not safe, right? Well, it's for parallel computing, who really cares? You're not caring so much about object persistence in the long term, you're caring about object persistence in the short term. I say security issues are RSA authentication of pickled objects and just only work on secure ports, and you don't have to worry about pickle, someone hacking your pickle or something like that. So in about 2009, I realized that what I had to do in front of me was basically serialize all of Python to make this work. So I started dill, and now it can serialize almost everything in Python. It can pickle code from the interpreter equally as well as from a file. You can save the entire interpretive session, which I showed. You can save edit to a Python objects dict, save classes by reference or definition. There you saw that I changed the class definition. I was still able to work with the objects. I have interrogation, inspection, diagnostic tools for pickling, and source code introspection and extraction. One of the things I'm moving toward is getting some neat features of Smalltalk, like what would you do with a saved session? One of the things you could do with the saved session is build a Python session with your functions in it, ship it as an image off to another machine. Matter of fact, you ship it to N machines and then have them all fire up and run. So now you have parallel instances like a virtual machine that have been set up, so you have a Python image. That works, but I'm working on the JIT. I have to be able to reconstitute the objects from code without changing their IDs. So that is still in the works. And I actually have a plan that stackless Python can do things like generators, and I'm just going to steal what they have and basically complete the rest of the language. Back at the time, I thought, wow, this is great. I can serialize most of the language. What happens now, most people aren't using dill, they're using pickle. So I don't have access to everyone's source code. I don't want to fork everyone's code. So I made this nice trick that when you import dill, it bootstraps into the dispatch table and loads all of the knowledge that it has, and then someone is using pickle, they're automatically able to leverage the dill tools, and you can serialize everything, even though you couldn't before. So I thought, hey, that'll do it, right? But it actually didn't work incredibly well because people use cpickle, or they'll have their own serialization mechanisms, and it'll break because of that. So the best thing for you to do is clear out your code and just use pickle or use dill, and things will work better. But like multiprocessing has its own versions of how to serialize, like a queue and whatnot. And to get around those things, and to let it leverage dill, I had to fork multiprocessing, MPI for Pi, parallel Python, RPyC, PyCUDA, and it was used to clear out some things in their code. Say if you have dill, use dill, and then basically I was able to do full language serialization for parallel computing on any of those kind of platforms, GPU, etc. And I released those as part of a collection of packages, pathos, dill, pyina. It was research grade about 2009, but then I could do heterogeneous maps with map of a function time of some object on the national labs and run things on a supercomputer in multi-way parallel. So it kind of worked. There was basically what I did is I wrote pathos and pyina to do a unified API for pool, so you can get asynchronous iterative blocking maps and pipes all with the same multiprocessing interface, so they're all exchangeable, and that means you can write code that uses a standard Python map and then just flip it out with multiprocessing or MPI or launching on a cluster scheduler, etc. Or running it over sockets. So that's pretty nice. It allows you to do very flexible, kind of computer scientists call programming models. So it allows you to just very easily change up the different parallel backends you want to use or nest them together. I'm planning to use ZMQ because IPython uses it, and I'm sort of integrated with IPython. I'd like to better integrate with IPython parallel. I have some other things planned for neater, kind of more efficient maps, like conditional parallel maps instead of asynchronous parallel maps. So conditional parallel maps would be, do you have enough information to be done? Therefore, don't wait for everything. So the abstractions in the programming model, as I was talking about, is basically, you can see it's the, there's MPI map, my model of something, so that'll run on Slurm in that case. So it's a configure a pool, get a map, and run on a map. And then the same thing with sockets, where I'm running over some machines, and you can mix these together. So you have heterogeneity and abstractions to do all sort of design work, and these asynchronous parallel maps. And like I said, I have a simple case for a conditional map. I can say 75% of the results are returned, so stop. I'm working on using statistics to determine if your results are good enough. But I need to do some more abstractions on that. I have a caching backend, so that says you automatically, when you run jobs, you can collect and archive the launched runs in a very streamless way, and that's this Klepto, this newer package that's only about a year old. What it does, it's a unified API for caching and archiving, and what it lets you do is have a backend of memory, file, memory map, directory, database table, etc. It's all the same API. It's a dictionary and a decorator API, so you can interface it like a dictionary to work with a table or a file system, and you can decorate a function so it caches the arguments and the outputs to the backend, and I use that as a go-between for extending parallel distributed computing with caching between, a number of processors or whatever the parallel arguments are. And so this is all made possible by serialization, right? This is something that Python as a standard can't do, but purely being able to serialize, the amount of work that went into the rest of this was very little. Most of the work was making Python serializable. So the immediate impact was I then also got another grant, $17 million for predictive science, where we now had a working global optimizer in this distributed parallel, and we started being able to do large-scale uncertainty and statistics as global optimization, and really challenge the frontiers of being able to do predictive science and build things like massively parallel optimizers. So this optimizer is a double-nested optimizer, where what it does is a global optimizer, and the optimizers are built as classes, and what it can do is, you can see I'm configuring the first step, torque map, and so I'm running it over a cluster scheduler, and at the lowercase, I'm building two solvers. I'm building a Powell directional solver, which is a steepest descent solver, and then I'm building another solver that says, I'm a buckshot solver, which is one of my solvers that says, I want to take 100,000 or whatever number of the steepest descent solvers and just go and have them run in parallel and just try to find the best answer as fast as possible, and then it all reports back and gives me, the best one or two or however they interact with each other. So I can, use parallel computing and optimization to do fast global optimization with steepest descent optimizers, or create other things like this to leverage parallel computing. All done because I can serialize the hell out of these classes that are, they have all sort of decorators in them and nice object-oriented, language constructs and inheritance, and I can pretty much use anything in the entire language and build complicated objects. I can serialize my whole optimizer and pass it off to another, put it in the database, pull it out, restart. I have full restart capabilities because I serialized the entire optimizer with the state and everything else in it. So that's nice. I can, I can have these start and then pass them off to another machine. It's cool. We are able to scale up large enough that I can do optimization over probability distributions, which means I have to, combinatorics, you have to try to find every possible scenario that's possible. I represent probability distributions by a basis set. So I have a lot of points. If you have enough points, you can represent any function. So I take like a probability distribution and I break it down into basis points, and it takes a lot of them, right? And so you arbitrarily represent any uncertainty function, like a probability distribution by these basis points, and sometimes it takes hundreds of thousands of them, and just let them run. And it can scale up and do optimization over these things. So I've run 1,000 parameter non-convex optimizations in parallel, where these are clouds of the different possible scenarios, condensing to the most likely scenarios at the end. So it's really basically the serialization of Python objects enabled this to happen, which actually allowed us to do all sort of new large-scale statistical science, things like validation of strength models on hypervelocity impact, more ballistics, statistics about ballistics, how materials would deform, real large-scale. So the interesting thing about the seismic problem is we would look at a tower and all the possible earthquakes, not pick one, the most likely earthquake, but all the possible earthquakes that were possible out of this earthquake generator to see if I could elastoplastically deform the truss structure. And because I'm doing all the possible combinatorics, the thing I get is, instead of the most likely case, which is when you get frequency matching for the tower, earthquakes knock down towers when they frequency match something. But you also get the Godzilla effect, which is like you get a big spike. And that's a rare event, but it happens. And what that does is just knock the tower down because it's enough of an impulse. And nothing else can predict that unless you go through all the rare event scenarios and look at the distributions without making a simple model. So that kind of thing allows me to do the same thing, like predict hedge or value at risk for portfolios in a stock market, right? It's the same kind of problem. And you can do this with optimizers, basically because dill allows you to serialize pretty much anything the hell you want. And you can turn Python into a very powerful parallel language. So, again, biggest things we've done is take a plasticity model like this, which has complicated physics in it. It's a parallel problem itself that's run on a bunch of machines. I tied together a kind of a prediction problem over 1, 2, 3, 4 petaflop resources on 3 national lab machines plus my laptop to run this calculation over 8 days to use a bunch of cores. So now our new challenge is working with the XMedX project, IBM, HP, etc., to build computing at the exascale, to design machines for that. The team is a bunch of Bell Prize winners. It's primarily C Fortran materials language, but it's driven by Python programming models and statistics. So Python can be used for HPC, but we need to make sure that object serialization is part of the language. I'll skip that stuff. What can we do? There's still a lot to do. It's a huge problem, and most codes really to be able to leverage this stuff, you have to rewrite it to leverage abstractions. That can take time, but if you can write your code to work with, instead of list comprehensions, a map function, you are ready to go. You don't have to. That's the nice thing, is I just code to map functions, and then my serial code works in parallel. So if you can do that, it's good. I would love to have this thing push and get into the language. I actually have asked in the past before, but that was before parallel computing was as much of a nice thing as it is now, and it's a little bit more accepted. And I would probably like to try to PEP again and see if we could do this. If you want to contribute, the code is at GitHub UQ Foundation. So all my packages are up there that I mentioned. And basically, don't settle for the state of HPC as it is now. Let's all try to fix it. So thanks.
Okay, questions?
You just mentioned there using map instead of list comprehensions. Can you elaborate on that and why that's needed?
Sure, because I can't make a list comprehension parallel, but I could make a map parallel. So if I write, the thing that I have is abstractions on map. So right here, if what I have is I have MPI, GPU, sockets, and it's all written to the multiprocessing interface. So if you build a pool and you can pick an asynchronous map or an iterative map or a blocking map, then all you have to do is overload the object. So I always write maps instead of list comprehensions.
That's a very nice talk, thank you. I'm afraid it's not an HPC question. I'm interested in serialization from a different point of view, which is testing.
Yeah.
So if you're testing an object, if you're testing something that changes state, I thought, wouldn't it be great if you could serialize the state you've got, serialize the new state, compare them, and see if the difference is what you expect. Yeah. So I'm interested in serialization of perhaps unknown objects for the purpose of testing.
Sure, that's perfectly a good thing to do. One of the things that I do is anywhere that Python serializes by reference, I also give you the option, actually the default is to not use serialization by reference. What I would like to do is give the user the option to serialize by reference or to serialize by saving the class definition. I can extract the source code of any object, and basically what I do is save the source code with every one of my classes or other objects. And therefore, if you serialize an instance, you also can get the source code. If you were here for the demo at the very beginning, I changed a class instance, serialized the object. I had a class instance, serialized the object, changed the class instance in the interpreter, then serialized the session, started it back up, and I had both old instance and new instance that were available, and I could compare them. So if you wanted to diff the byte code, you could, or if you wanted to diff the source code that I can extract from the object, I could do that as well. I don't have a built-in differ, but I have the ability to get the source code out of any object.
How does it work with native code, C objects? And
with C objects?
Such.
That's a problem, right? If the Python can handle the C object as an embedded object by reference, I can do it too. But if you're actually trying to serialize a C object, it doesn't work. I mean, what's that? Yeah. I mean, if you have it in a file, a file reference, that's fine. But if you're building the object dynamically in the interpreter, and
is there something written on that one?
Object, no. It may not work, and that's still part of what I would have to take care of. So like NumPy array will help that? No, NumPy array is fine. I mean, that's because it has a Python layer. There's only certain objects that don't failing to, and they're usually because they have part of the C instance or reference to the C.
It's just not detecting it.
But
sometimes it doesn't.
There's only actually two cases that I can't handle, and one of them depends on a C native bit. That's not for everything, but it's just for some of the objects.
Let's see if this projector is varied.
Anyone else? Questions? Thank you very much, Mike.
Thanks.